let's talk about one of the absolute cornerstones of statistics, randomness. Now, it sounds simple, doesn't it? You just pick something at random. But it turns out that real statistical randomness is way more precise and, frankly, way more powerful than you might think. Getting it right is the secret to getting data you can actually trust. So here's our game plan. First, we're going to bust a super common myth about what random even means. Then we'll get into the official definition, what tools you'll need to do it right, and the exact 3-step process to pull it off yourself. And we'll wrap up with one final crucial detail that really changes things. Okay, let's just dive right in. First things first, we kind of have to reset our brains on what the word random means in the world of statistics. Because it's not about chaos or just being unpredictable. It's much more structured than that. Let me throw a little thought experiment at you. Picture a classroom with 20 students. It's perfectly balanced, 10 boys, 10 girls. Now, to pick a sample of 10 for a survey, you just flip a coin. If it's heads, you survey all the boys. If it's tails, you survey all the girls. Simple enough. Now, here's the question. Is that a random sample? Think about it for a sec. Every single student has a 50-50 shot of being picked, so it has to be random, right? Well, if you said yes, you just fell into one of the most common traps in statistics. And the answer is a big, fat no. And this is so cool because it shows where our brains get it wrong. We focus on the individual person. We think, hey, every kid had a fair shot, but statistical reality cares about something else entirely. It's not about every person having an equal chance. It's about every possible group having an equal chance. And this is where all falls apart. In that coin flip scenario, what was the chance of picking a sample with, say, 5 boys and 5 girls? It was 0. Zilch. It was literally impossible. Same for a group of 9 girls and 1 boy. Any mixed gender group had no chance of being selected. And if certain combinations have a 0% chance of ever being picked, then your system just isn't random, period. So if that clever coin flip idea is a total bust, what's the right way to do it? Let's get to the good stuff and look at the official definition that fixes this whole problem. And there it is in all its glory. Simple random sampling, or SRS for short. All it means is that if you need a sample of 10 students from that class of 20, then every single possible group of 10 has the exact same chance of being picked. The group with the first 10 kids on the list has the same probability as the last 10 kids or a group with 5 boys and 5 girls. Every single combination gets a fair shot. That's the real key. And this quote just nails it. This is why we're so obsessed with getting the definition right. True randomness isn't messy. It's a careful, deliberate process. And honestly, it's our best weapon for defeating bias, for taking our own hidden assumptions and preferences out of the equation and letting the data speak for itself. Okay, so before you can actually do a perfect, simple, random sample, you need to get your tools in order. It's a little prep work, but it's absolutely essential. We're talking about something called a sampling frame and some really simple notation. First up, and this is the big one, you need a sampling frame. Just think of it as the master list, the ultimate roster. It's a complete list of every single person or thing in the population you want to study. If you don't have this, you're pretty much dead in the water before you even begin. You know why? Because a bad frame means you're guaranteed to get a bad result. Here's a classic example. Imagine trying to survey all city residents today by using a landline phone book. It would be a total disaster, right? The bias you'd introduce is called undercoverage. You'd completely miss anyone with only a cell phone or no phone at all or an unlisted number. Your sample would be wildly unrepresentative of the actual city. All right. Next up in the toolkit, some super simple notation you're going to see all the time. Big N is your population size. That's the whole shebang. Everyone on your master list. And little n is your sample size. That's the smaller group you're actually going to collect data from. That's it. Big N, little n. Easy. Okay, we've got the theory down, we've got our tools ready. So, how do we actually do this? Let's walk through the simple 3-step recipe for conducting a true, simple, random sample. And honestly, it really is this easy. Step 1, you take that sampling frame, that master list, and you give every single person a number, starting from 1 all the way up to big N. Step 2, you fire up a random number generator. Literally any spreadsheet program can do this, and you tell it to spit out n unique numbers. Step 3, you just match those random numbers back to your numbered list. Whoever's number got picked, congratulations, you're in the sample. That's it. Clean, simple, and truly random. We are so close to the finish line. There's just one last little detail we need to cover about how we pick those numbers. It sounds a little nitpicky, but trust me, it matters. And it's this idea of sampling with replacement versus without replacement. With replacement is like drawing a name from a hat, reading it, and then putting that name back in the hat. That means the same person could get picked again. But for simple random sampling, the gold standard is without replacement. Once your name is drawn from the hat, it stays out. This just ensures that every person in your final sample is a unique individual. And this makes total sense, right? It means the odds change slightly with every pick. If you start with n people, the first person picked has a 1 in n chance. But for the second pick, there's only n minus 1 people left in the hat, so their odds are now 1 in n minus 1. The pool gets a little smaller each time, and the odds for everyone who's left go up just a tiny, tiny bit. So why do we go through all this trouble? The definitions, the frames, these picky rules about replacement? It's because when you follow these steps, you are building the strongest possible fortress against bias. A true simple random sample creates what is basically a perfect miniature version of your whole population. And that means the conclusions you draw from it have the best possible chance of being dead on accurate. So I'm going to leave you with a challenge. Now that you know how to spot the difference between real randomness and stuff that just feels random, start looking for it. Where do you see it in your daily life? Think about those person-on-the-street interviews or online polls or TV call-in shows. How often do they create a totally biased, skewed picture of reality? Once you start to see it, you can't unsee it, and you'll become so much smarter about the information you consume every single day.